So just so you guys know, I am recording this lesson. I just started it. And today we're going to start talking more in-depthly about electrons. And the reason for that is electrons are why everything bonds. Electron configuration represents the address of where electrons are. And if it's like, well, what does that matter? Remember that as we were learning about the atom, we said, okay, those protons and neutrons are hanging out in the nucleus. They have an address. They hang out in the nucleus. Like they're all in one little apartment building there. But the electrons live out in the suburbs. There's streets and all sorts of things there, and layers and levels. And so we need to know where those electrons are because that's going to affect how well an atom can bond with another atom and whether they will bond at all and who they will bond with. So, super important there. If you want to get out your periodic tables that you drew on last time, you can. If you want to open up this periodic table, remember this is the guy that I recommended to you, and you'll see here there's a little cheat tab that talks about electrons and things like that, and we're going to be learning all about what this means and doing these and all sorts of things. So if you want to have that guy open on your laptop, you can, or you can have your paper periodic table out. I am going to give you another periodic table today for us to like color and draw on and things like that. That's coming in just a little bit there. All right, so I've been badly drawing. These rings for our energy levels, and here we go. Here we're actually talking about them. So we have the nucleus in the center. We call these energy levels N. Closest to the nucleus is N1. The next energy level is N equals 2. Next one is N equals 3, 4, 5, 6, and 7. 7 is our highest energy level at this time that we are aware of. And if we actually go to the periodic table and look, right, we said that our rows going up and down represents energy levels. And if we count, we have 1, 2, 3, 4, 5, 6, 7. And so our periodic table is even set up for 7 energy levels so far. And if you're wondering about these guys down here, we'll talk about them in just a little bit. The closer electrons are to the nucleus, the less energy they have. They're more stable. Remember that electrons are negative, and the nucleus is positive. So there is an attraction both directions that those electrons want to be as close to the nucleus as possible. The further out they go, the less stable they are and the higher energy they are. They don't want to be at a high energy level. So my analogy here is this electron here is like someone standing on the ground. They're solid. This guy out here would be like someone standing on the top of the building, on the roof of the building, looking over the edge, very unstable, right? A lot of potential energy. Down here, lower potential energy. And this will become very important in our flame lab. And it's really important for why we have lights and everything else going on there. So the further an electron is from the nucleus, the higher the atom's energy level. They range from 1 to 7. The The higher the number, the further from the nucleus. Pretty logical so far, right? All right, so we have sub-levels. So we talked about we have these 7 energy levels there. Well, there are sub-levels that go with these energy levels that tell us about the shape that an electron is moving in. We draw these circles like this because, you know, we're working on a 2D surface, a piece of paper or a laptop, when really electrons are moving in 3D shapes. The other thing that we have to keep in mind is electrons, while trying to be close to that positive nucleus, are trying to avoid each other, right? They are all negative, so they don't want to be near each other. Just like magnets, right? We know magnets, the 2 polar ends, if you have, you know, one magnet, we call it north and south, right? These guys are going to be attracted to each other, but if we flip this magnet around, they're going to repel each other. It's because of the electrons in the magnets. So the weird thing about electrons is we don't know exactly where they are. Has anyone ever heard of quantum physics? A little bit, right? If you watch Big Bang Theory, they talk about it a lot. So the deal, this is where physics and chemistry have a nice overlap for people who are thinking about going into physics. The thing about electrons is they're almost pure energy. So when you go to look for an electron, the only way for us to be able to see it is to hit it with energy, like an X-ray. Well, the problem with when you hit energy with energy is it makes energy move. So it's kind of like looking for a balloon in a dark room. Let's say all the lights are off, you can't see anything, and you blow up the balloon, and it's in the room somewhere, and you're trying to find it. Well, your own air is going to make that balloon move away. Or if you've ever been in a pool or you've tried to swim towards something and grab it and it keeps pushing away because of your motion in the water, that's how electrons are. So we only know approximately where they are, the highest probability of where they are. We have seen them with X-rays. Like we said, they move as soon as we hit them with X-rays. Each sublevel can hold 2 electrons. And if this sounds like, wow, this is a lot of information. There's 7 energy levels, there's 4 sublevels, there's 2 electrons in each sublevel. The periodic table has all this information for you, and I'm going to show you how to find it so that you're not memorizing this. All right, so just for fun, first off, our first energy level is the S orbital, and that stands for a sphere, and the electrons are moving in a spherical fashion. So in the S energy level, we have 2 electrons in that energy level. Our next one is our P sublevel, and it's dumbbell shaped, and we have 6 electrons. Because really how this looks, this is only one of the orbitals. And actually you have 2 electrons going this way, 2 electrons going this way, and then this is where I can't draw it. And then we would have 2 electrons coming out, and then behind, like, so that we have it in 3D shape. So 2, 4, 6, that orange one would be like coming out of the board and going into the board, that Z plane. Right, so maybe you know this from math. And then we have Z going out and in to the board. So that's the P dumbbell. And then D, we have propeller, where we're going to have 10. And F, we're going to have 14. So here we see neon. We're using neon as an example. Here's the nucleus. Here is our first energy level, and it's an S shape. Here's our second energy S shape, and then we can see that we have those P dumbbells. So here's 2 electrons, here's 2 electrons, here's 2 that would be going across, here's 2 that would be going across, and here's 2 that would be going across. So we see that we have 2, 4, 6, 8, 10 electrons. We look at neon, and we see in its neutral state, 10 protons, 10 electrons. So, about to talk about this, but as we look at neon, look what we have. We have 1, 2, that first energy level. There it is. Then we have our second energy level. 1, 2. There's that second energy level. And then here we have 6 electrons. 1, 2, 3, 4, 5, 6. So we're already starting to see a little pattern here. 2, 2, 2, 6. And that's why we look at neon at the end there. All right. So we have 4 sublevels. They're called S, P, D, and F. The number of orbital types in S, we have 1. It's the sphere. In P, we have 3. In D, we have 5. And in F, we have 7. Well, if there's 2 electrons in each orbital, then that means we have a maximum number of electrons in each level. Let's look at the periodic table. I'm going to actually hand out these now so you can start. These are blank without elements for a reason so that you can take notes right on them about electrons and not worry about actual elements. We don't care about the protons right now. If you want to get colored pencils, you can. They're back here on the shelves, or get your own out. Coloring this might help as we're taking notes. We're going to see a lot of patterns. And if right now you're like, I don't understand any of this, it's actually about to become much clearer because we'll see the patterns in the periodic table. Would you like a charger? You don't have one of those on the back shelf or that box. Oh, you do. And there should be an extension. Did everybody get one? All right. Don't get frustrated. We're like doing this right now on our learning, and we're gonna roller coaster it. So don't get frustrated. Keep going. It will make sense. Okay. So we have these energy levels. One through 7. And then we have sublevels within those energy levels, which are S, P, D, and F. And these guys tell us the shape that the electrons are moving in. Then we have orbitals. S has 1, P has 3, D has 5, and F has 7. And we know each orbital has 2 electrons in it. So that means that S has 2 electrons, P has 6 electrons, D has 10, and F has 14. And I'm just writing this so that we have this cheat sheet even after I change the screen. Yes, sir. The orbital is how many we have within it. So if we go back, this is a great example. So S, spheres, that's it. That's what they look like. But actually, you know what? Let me find, hold on one second. I want to find a better picture than what I'm drawing. Even that's even better. Come on. Here we go. So see, this is that's what I was trying to draw. They do a better job, right? So an S is just one orbital. Here's a singular P orbital, but P's come together to have 3 of them. Black, here they're showing it black, red, and blue. So you have 3 of them. D, let's see if we have a D. Okay, so here's D. So here's what one D orbital looks like, but they stack so that there's 5 of them. And then F, so that there's 14 of them. So each orbital, each sublevel has a shape, but some of them come together multiple times. So spheres, you only have it come together once, but P, the dumbbell, they'll come together 3 times in that geometric shape. Because the original names are in Latin and start with different letters in different languages. Yeah. I have to tell you, every year someone asks that. All right. So I made this little cheat sheet here on the side so that we can look at this. And this is where your own paper periodic tables come into play. I'd like you to color code, write on them, take notes, whatever you need. So if you're like, wow, this is a lot to remember, you don't need to remember it. The periodic table has it. So first off, our energy levels are right there. 1, 2, 3, 4, 5, 6, 7. And on most of the periodic tables, you're going to see, or I'm going to hand you, whether it's the original one I gave you, or it's this green one you borrowed, or the blank one you have right now, you see the numbers written along the side. So right here, these guys, I should have written this over a little bit. These numbers are our energy levels. Actually, I am going to erase it, and I'm going to label it right on the periodic table. All right, so these guys right here are energy levels. Our S, P, D, and F are sublevels. and each sublevel has 2 electrons. Watch what happens. Here's sublevel 1. Sublevel 1, so hydrogen equals sublevel 1, S, and it has 1 electron. So this shows me it has 1 electron in sublevel S, 1 electron. Helium, still energy level 1, still S. He's the only one that's an outsider there. 1 S, but he has 2 electrons. That S is now full because remember, S only has 1 orbital. Each orbital holds 2 electrons. So now we go to these guys. Lithium has this still, right? Because we build as we go across. So lithium has 1s2, but now it has energy level 2, S subgroup, 1 electron. 2 plus 1 is 3. It has 3 electrons. Beryllium, also energy level 2, so it still has this. Still an S, but it has 2 electrons. Remember how we talked about that the columns all have the same number of valence electrons? Everything in this column, right, is going to have an S1. It's going to have an S with 1 electron. These guys have S2, S orbital, and it's full with 2 electrons. But here's where we don't have to remember things. As we go across from beryllium and we go over to boron, we now enter that P sublevel. We're still in the 2nd energy level, but now the electrons are moving in a different shape. This electron, these 2 are moving like this. Then we add this electron, and he starts moving like this, and the same energy level. So these guys are moving here. This guy is now doing a dumbbell. We add 1 more electron. Now it's doing a dumbbell. There's 2 doing a dumbbell. Add 1 more. Now we add a dumbbell in the other direction. And they keep overlapping each other. And we're thinking 3-dimensionally. So P has 3 orbitals. 1, 2, 3. 6 electrons. There's 2 electrons in each orbital. P has 3 orbitals. So P has a total of 6 electrons. So when we look at neon, like we did in that picture, we see that neon still has 1 S2. Then we come here, 2 S2. And then we come here, we're still in the 2nd energy level, but we're in this block, so it's P. And it goes 1, 2, 3, 4, 5, 6. And if we count up the number of electrons, because these superscripts are the actual electrons, so this is our number, this is our actual electrons, 2, 4, 10. Neon has 10 electrons. The big numbers are the energy levels. Whoops. And the letters are sublevels or shape. So we have a lot of information in this address. And this is electron configuration. And this tells us how well something's going to bond, who it's going to bond with. As we come along, we go to sodium. Sodium would now be 3s because it's in this group, 1 because it's in the first column. Everything in this column will be whatever energy level, S1. As we go into the second column, whatever's here will be whatever energy level, S2, because it's in the second column. And then as we go across here, we have 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, and then the p's are done there. And we have to come back to the beginning. And this guy, his valence electron is 4s1, because he's in the first column. We're still going up. It's okay. You know what's great is I love, like, right now you guys are like, what? This sucks. And, like, seriously, by the end of the period, you're going to be like, you will. Trust me. What's up, Nate? How do you, what?
How do you like energy levels?
How do they relate to each other?
Yeah.
Hold on 1 second. I can only draw this so well, so I'm pulling up something I know that will work. Although I might make my computer explode in the meantime. It's pretty unhappy with me right now. I will keep looking. I know I have a really good visual of them like actually spinning on each other, and I can't find it right now. But they're, I mean, if you go back to, I'm laughing at myself. So I always hate when teachers do this. They're like, I'm just going to say the same thing over again, and that's going to make you. So if we were just looking at helium, we would just have this, because helium is one energy level, and it's a sphere shape. So this would be just helium. If we were looking at lithium or beryllium, it would be this and this, because we have 1s, and then lithium and beryllium is 2s. And then when we get to boron and carbon, we would have this, this, and one of these guys. Only one orbital. And then as we go to nitrogen and oxygen, we would have this, this, and two orbitals. But that third orbital would be empty until we add, to go to fluorine. Fluorine would bring that third orbital in, and then neon, we would add another electron there. And so it builds on the shapes. And then when we go to sodium, which is 3s, bigger circle. We would have another sphere over the top. So these are still going on. These are those inner electrons all going on. And then when we go, okay, now we're going to look at sodium, that's going to have a bigger sphere. Actually, much bigger than that, but just my board. All right, and sodium and magnesium, so that would be sodium spinning around. Magnesium would add another one spinning around. And then when we went to aluminum, we would gain another p orbital. Because aluminum is 3p1. And then if we look at sulfur, it would be 3p2. So you still have that stuff inside. Okay, that should really cross. That should really cross at the nucleus. There we go. So here would be sulfur, and then when we go to phosphorus, we're going to gain another p orbital. And then when we look at sulfur, that electron goes there. And then when we look at chlorine, we gain our third p orbital. So this would be 3p5. 1, 2, 3, 4, 5. And then when we finally go to argon, boom, and the whole thing's full. And then we would go back to look at potassium. We would add the fourth energy level. And we would just keep doing this. Yes. That's actually not too bad considering I'm growing up for it. I just want to say. I love how, like, I've taught this a lot, and every year I get pushed to think of it and teach of it in a different way. All right, we're gonna keep pressing forward. The next slide, also helpful. Another way to look at this, and piggybacks very nicely on the drawing that Nate just had me do, because it brings us to talking about that energy again. All right. So just like with protons, we read electrons going across our periodic table. Notice I don't have elements here. I'm not caring about the elements right now. I'm caring about how these electrons build. So here's our energy levels. Ready? 1, 2, 3, 4, 5, 6, 7. And we have that S block and P block. Everything in here, valence electron-wise, is going to have one valence electron. So whatever is here, I don't care what it actually is going to be 3s1 as a valence electron, outer electron. It's got ones underneath, but the ones that will bond are 3s1. Whatever is here, whatever it is, 3s2. And then I go across here, 3p1, 3p2, 3p3, 3p4, 3. And then I'm full. So remember how I said you don't have to memorize that P has 6 electrons. That's right there on the periodic table. Just count. 1, 2, 3, 4, 5, 6. Oh, I hit the end. The P's are done. And it's also shaped very nicely to remember where things are. So here, come back to the beginning of the sentence. Valence electron, 4s1, Or S2, and then we hit D block. I haven't talked about D block yet. Notice that the energy level for D block is 3 when we are in the 4th layer. So this goes back to that drawing that I was drawing. How you remember it is drop down D. That's the mnemonic device. When you get to D block, drop down D. And then F is fall even farther, F. My little mnemonic devices. I know you love them. So what is happening here is that atom is getting bigger and bigger and bigger. Now remember we talked about electrons are negative. All they want to do is be with that positive nucleus. Oh, I love those protons. Oh, I want to be as close to you as possible. But they hate their sibling electrons. Ew. Get away from me. I don't want to be with you. So what happens is when they're close to the center of the nucleus, it's smaller. There's not as much room down there. So they keep trying to find ways, right? So here's the nucleus. So these guys are going to be here. And then it gets a little bigger. And then here's energy level 3. So far the electrons are being able to be as close to the nucleus as possible while being as far away from each other as possible. And that's why they take the shapes that they do. Think of this as, I know some siblings get along. Some siblings do not. You know, I have 5 kids. There's all kinds of variations there of who gets along with who. They want to be as close to their grown-ups as possible, but as far away from the sibling as possible. And they keep doing this until we get to energy level 4. And then what happens is it's so big, there's room for them to bring more in at this level. And that's why D is after 4. 4 has to happen before D can happen, and they fill underneath 4S. But once D is full, so we add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, the third energy level goes, nope. Now we're really full, and it goes back to filling the P level at the 4th level. And it will go back to putting those P's in there. So these guys, this is 3D1, 3D2, 3. Now I'm only writing the valence electrons. The other electrons are still there. Okay. Again, you did not have to memorize 10 because the periodic table is very nicely only 10 blocks across. You know when to stop. You hit a wall. And then we continue, but now we're back to the 4th energy level, or P1, or P2, or P3. Boom. And then we go back to the beginning. Now these guys, I want to make sure I get it right. I always goofed this up, so I want to make sure I get it right. Goes in 1, 2, 3, 4, 5. Right. These guys, right, because it goes in, really go in here. Now the reason we drop them down, if you're like, why do you have 2 periodic tables? This is actually how the periodic table should look. This right here is this. They do this so that it fits on the screen or on a piece of paper, because because this does not print. So really what we have is it goes from number 56 to 57 and so on, and then 70 to 71, and then to 72. So these guys, it ends like here, 56, goes to here, and then comes back. So it really should look like that. And so here's our S block. This low level is our F, and if we count, there are 14 across. Again, we don't have to memorize that number. The periodic table gives it to us. And then we get to our D block, which is 10, and then to P. And the F also falls down. So the F goes down in energy level 2 because, again, we've made that atom so big. I mean, think about it. 57 protons. 57 electrons. Picture 57 siblings. All right? They want to be as close to the household as they can, but not when the other sibling is there. If you had 57 siblings, you'd probably feel the same way, right? So for D, we drop down 1, but for F, we drop down 2. So we go from 6S down to 4F, because it's dropped down 2, and then we come back to D, and we do the D, and we do the 6. And that guy's always up there, so you can always also use him as a reference. No memorization. We're going to learn to use it. We're going to use it. We're not memorizing all these little numbers. We're going to understand how to use it. And what's great about this is the Y is huge. This is going to be how we make molecules and how we cause chemical reactions. So right now we're just learning this stuff, but we're going to actually use this to go, okay, I want to make sodium chloride. I want to make potassium nitrate. I want to make acetic acid. This is how we figure out how to make these things and what's going to react with what. All right, so this is what I've been drawing over there. The first one's the energy level. Then we write the sub-level. And then the superscript is the number of electrons. So I drew that way back. Energy level, orbital, and the number of electrons. So let's do some. I think the next one, yeah. Let's do some. Yeah. There we go. All right. So, nitrogen. We're looking at our periodic table. Does anybody want a periodic table with actual elements on it? Or do you have them? You have yours. Does anybody want? Because the blank one is more for you to write notes on and get a vibe. But if you want actual, we'll do that. All right. So nitrogen. We're going to read across the periodic table. And this is where, as we practice, we're going to go, okay, application is better than being lectured at, but I had to give you the foundation there. All right, so we want to get to nitrogen right there. So we're going to go across 1s2. So 1s2. Oops, not going to trip. 1s2. That layer is full. So we go to the next sentence, the next line of our readings. Energy level 2, 2s2. We haven't hit nitrogen yet. So we write 2s2. And then we keep going. Oh, finally to nitrogen. We're still in the second energy level. We're in the P section. 1, 2, 3. So it's 2p3. That's the electron configuration for nitrogen. And we can double check it by saying nitrogen has 7 protons, so I need 7 electrons. 2, 4, 7. I can count those superscripts, and they should equal the number of electrons that I need. Let's look at calcium. So calcium, got to start at the top. 1s2. I go along. 2s2. Now calcium is not in this section here. So I can just write 2p6 because I have all of those electrons are there. Boom. Come to the third energy level. No calcium there. So I can write 3s2. Keep going. I don't stop till I get to calcium. Go across. Calcium's not there. So I can write 3p6. Whew. Energy level 4. I hate calcium. So 4s1, 2. I'm going to double check that I did a good job. 2, 4, 10, 12, 18, 20. Calcium's number 20. 20 protons, 20 electrons. How many valence electrons does calcium have? How many are in the outer layer? 2. There's 2 ways we can tell now. The first one is, we know that everything in the second column, does that take number 2 up there, has 2 valence electrons. Everything. So boom, we know it has 2 valence electrons. The other way is, if we look at the electron configuration, we go to the highest energy level. It's going to be the outermost shell. I see 4. There we go. So now we have 2 ways to see how many electrons are on the outside, and that's important because that determines how attractive calcium is to another atom. They judge each other by the cover of the book there. What electrons are you showing me? All right, gallium. Gallium, where are you? Oh my goodness. There's gallium. All right, well, calcium's here. I love this part. Calcium's right there. So I already know that gallium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I know that much. And hopefully right now you're going, oh, because, right? Calcium is on the way to gallium. So all I did was copy calcium. So right now, if I stop right here, I'm at calcium's electron configuration. But I need to go a little further. All right. So now I go to D block. D, drop down D. So that means that I have to go to the third energy level. And I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So 3d10. Gallium's the very next one, so it goes back to 4p, and it only has 1 electron there. All right. How many valence electrons does helium have? You are correct. It has 3. 2 ways we can tell. Well, actually, 3 ways we can tell. One is we can go, okay, 1, 2, 3. Or we can look up here at this guy, and we know that 3 there, the one column, tells us that there's 3. Everything in this column has 3 valence electrons. Or I can look here, and I can go, okay, where are my largest numbers? Why do I only have blue markers? I don't know. All right, I see a 4, and I see a 4. So that means there's 1, 2, 3 valence electrons. These are both on the outer level. This is inside. Yes, you can write this over here. Some people like to clump, and they'll put 3s2, 3p6, 3d10, and then write their 4s. That's fine. Either one is fine. It's just a personal preference. I wouldn't mark it right or wrong or judge you on that or anything. All right. Who do we have right there? Much easier this direction. Who is this? Simon. Cobalt. How did you get that, Simon? I love it. He went the shortcut route. He looked right here, and he just went to 3. Right? Well, it's a D, so he knows he has to be here. So this is 3. And so he went 1, 2, 3, 4, 5, 6, 7. Cool. So that's the super shortcut way. Another way you can do it is you can add up the electrons. Right? And we can also get there, and if we add those electrons up, there should be 27 of them. So again, multiple ways to get to information. All right, I think it's time for us to breathe and do a little practice. Not collected, not graded, but we're going to do it. If you want to work together, collaborate, you can. I will go over this. I want you to try it on your own. Ask me questions. Ask your elbow partner questions. Look at your notes. You take 12. Yeah. It's only illegal to get caught. See, Henry agrees. Then I wow, good notes. She copied off me. Yes, she did. Good notes, Abby's. Yeah, thank you. You're welcome. All right. We're going to pause this. All right, so here we are back going over our work. I love this worksheet because it also gives us some review of thinking about charges, and obviously that's going to be really important because that's that bonding again, right? Fluorine becomes -1 when it bonds with something and it gains that electron. So charges are going to be like a huge part of our lives in chemistry. Yeah. All right. So charge, -1, number of protons, 9. We get that off the periodic table. Fluorine has 9 protons no matter what. But we do change our number of electrons because it has gained an electron because it's part of a relationship and someone has given it an electron. Normally, if it was neutral, it would be 1s2, 2s2, 2p5. This is if it were neutral. Okay? But with a -1 charge, It is 1s2, 2s2, 2p6. Because it has gained 1 electron. Nate, play nice.
Yeah, Nate.
Alright. But whoever wrote this, I have to say thank you because it helped me teach that and make a point of that. Alright, -2. Sulfur has 16 protons no matter what. Correct, we have gained 2 electrons for a total of 18. So sulfur, normally, again, this is neutral. What is going on with my blue markers? This is neutral, would be 3p4. And notice, I don't have these memorized. I am looking at the periodic table. I don't have these memorized. 3p4, but it has gained 2 electrons. So with a -2, so S2 negative would be the same stuff, except it would be 3p6. Next up, phosphorus, -3, 15 protons, 18 electrons. We're doing great with that. Phosphorus, again, this would be if it were neutral. I'm going to change colors again. This is if it's neutral. Would be 3p3, but it's gained 3 electrons. So 3p6 is for phosphorus with a -3 charge. Potassium +1 has 19 protons. Very good job. Whoever did this, we love when there's a +1 to say, oh, it's gained a proton because it's +1. Protons are positive. Gain a proton. No. Excellent job there, keeping it with 19 protons, but it did lose an electron. So that's why it's positive, because remember, this is the pluses and this is the negatives. So if we -18, or 19 minus 18, whichever you want to look at, is going to equal +1. Good with the math there. Neutral potassium is 4s1. But potassium with a charge would be, and I'm going to write the whole thing out, 2p6, 3s2, 3p6. That fourth energy level is gone. All right, we're going to pause for a second here and have a bigger moment. What is a trend you're noticing with charges and the electron configurations? And this isn't like what we're learning right now. This is us extending and thinking ahead and bigger picture. Lucy. It affects the last number. How does that last number look now? Fluorine is here. -1, right? Electron-wise, it's still fluorine, but electron configuration-wise, it's now here, right? What was the next guy? Sulfur. Sulfur's here. -2. Electron configuration-wise, it's now here. Next guy is phosphorus, here. We're saying -3. Electron configuration-wise, it's now here. Potassium. We didn't make it negative. Notice we made it +1. It lost an electron. When it loses an electron, electron configuration-wise, it's now here. Did we notice the terms there? Notice these numbers aren't, I'm not just randomly going, hey, let's make it -1, let's make it -2. They are gaining and losing electrons so that they end up in this noble gas range. They end up with a final outer full shell. If they're over here, they've got 1 or 2 hanging out, they lose them, become positive. If they're over here, they have spaces, holes, gaps that they want filled, and they gain electrons to get here. So we're already starting to see a big trend here. All right. Did we like, yes. We learned from our mistakes. We're seeing the trends. So do we feel like we went over the roller coaster hill a little bit? Like the pattern is at least there, even if you're not sure of it, you're like, okay, I at least see that there's a pattern there. All right. Not gonna assign homework because I don't want to. All right. Next class, we will dig a little deeper and hopefully have our fire lab.